Assalamu alaikum students. Today we are going to start our new topic, that is the nucleophilic aromatic substitution. But before going to discuss in detail the nucleophilic aromatic substitution, we will discuss aromaticity, that what is the aromaticity. The topics to be discussed are nucleophilic aromatic substitution, aromaticity, SNAR reaction, SN1 reaction, and benzene reaction. What is aromatic nucleophilic substitution? Like till now we were discussing the nucleophilic aliphatic substitution. Now to discuss the aromatic nucleophilic substitution. A nucleophilic aromatic substitution is a type of organic reaction in which the nucleophile displaces a good leaving group such as an halide on an aromatic ring. These reactions, the nucleophilic aromatic substitution, can follow two very different paths. One is the bimolecular displacement mechanism for activated aryl halide, and the second one is the elimination addition mechanism, which involves the remarkable intermediate called benzene. Aromatic rings are generally electron-rich, which allows them to attack electrophiles. To facilitate attack by a nucleophile, a ring must be electron-poor. Why? A ring must be substituted with a strong electron withdrawing group. There must be a good leaving group, and the leaving group must be positioned ortho or para to the withdrawing group. We must investigate these things. To be classified as aromatic, a compound must meet both of the following criteria. It must have an uninterrupted cyclic cloud of electrons, often called a cloud, above and below the plane of the molecules. What this cloud means, or what is this? For the cloud to be cyclic, the molecule must be cyclic. Okay, like we have seen that for aromatic compound, there are these conditions or these criteria, that it must have an uninterrupted cyclic cloud of electron. Cyclic cloud. So, for the cyclic cloud, it is must that the molecule must be cyclic. This is the first condition. For the cloud to be uninterrupted, every atom in the ring must have a p orbital. Because this cloud is due to the electron in the p orbital, so every atom in the ring must have a p orbital. For the cloud to form, each p orbital must overlap with the p orbital on the other side of it. The p orbital must be overlapped with the p orbital surrounding that on both the sides. So, and for this surrounding, when this will be possible, or for this overlapping with these two orbital of each side, therefore the molecule must be planar. And the cloud must contain an odd number of pairs of pi electrons. So these are the conditions. If a compound meets these all conditions, so that will be aromatic. Under normal conditions, aryl halides do not undergo nucleophilic substitution reactions. They are less reactive towards the substitution reaction by nucleophile due to the, in case of alkyl halides, the carbon of CX bond is sp3 hybridized and its bond length is 177 picometer. In aryl halides, the carbon of this carbon halide is sp2 hybridized. Its bond length is 170 picometer, which is shorter than the 177 sp3 hybridized carbon bond length. So shorter the bond length, stronger is the bond, and more energy is required to break the bond. The second reason is the lone pair of electrons of halogen atom is in conjugation with the pi electron of the ring. The lone pair on the halogen, the lone pair of electron on the halogen makes conjugation with the pi electron that are present in the cloud of the ring. Due to the resonance, the carbon-halogen bond in aryl halides possesses double bond character. As we know that there is a resonance present and the carbon and halide bond are in between a single and double bond, and it possesses the characteristic of both a single and double bond, and that's why it is stronger than the carbon halide bond in the aliphatic compounds or in the sp3 hybridized, and they are less reactive toward the substitution reactions. What is aromaticity? Benzene. If we look into the benzene, benzene is the simplest aromatic hydrocarbon. Benzene has 4 degrees of unsaturation, making it a highly unsaturated hydrocarbon. Whereas the unsaturated hydrocarbons such as alkene, alkyne, and dienes readily undergo addition reaction, benzene does not. Look into this example. It's an addition product. But in case of benzene, there is no reaction with the bromine. What is the criteria of aromaticity? That is Huckel rule. 4 structural criteria must be satisfied for a compound to be aromatic, that we have discussed previously also. Number 1, a molecule must be cyclic. Like these are the cyclic compounds, benzene, and every p orbital with overlap with the 2 neighboring p orbitals. This overlap with this one and this one, this overlap with this one, and so on. This is aromatic. Acyclic compounds. There is no overlap here. 1,3,5-hexatriene. There can be no overlap between the p orbital and the 2 terminal carbons. Here. This is 1,3,5-cyclohexatriene, 1,3,5-hexatriene. It has again the 3 double bonds, but on the 2 terminal, these carbons, these p orbitals cannot overlap with each other. So to be aromatic, each p orbital must overlap with p orbital on adjacent carbons. The molecule must be planar. All the adjacent p orbital must be aligned so that the pi electron density can be delocalized. They should be planar and should be aligned with each other, and the density should be distributed delocalized over all the carbons, over all the atoms. This is the cyclooctatetraene. It's not aromatic. A tub-shaped 8-membered ring. This is adjacent p orbital cannot overlap. Electron cannot delocalize because these are not planar, so they cannot overlap with each other. But against this, benzene is planar and all the p orbitals are overlapped with each other. Since a cyclooctatetraene is non-planar, it is not aromatic and it undergoes addition reactions just like those of other alkenes. It is not planar, it is not aromatic, and it can undergo normal addition reactions with bromine. A molecule must be completely conjugated. There must be complete conjugation. An aromatic compound must have p orbital on every atom. Every atom must have p orbitals, so that should be, and it should be conjugated. Here, benzene, completely conjugated ring. Benzene, a p orbital on every carbon at aromatic. Every carbon, so is aromatic. 1,3-cyclohexadiene. There is no p orbital on these two carbons, so not aromatic. 1,3,5-cycloheptatetraene, not aromatic, because there is no p orbital on this position. A molecule must satisfy Huckel's rule and contain a particular number of pi electrons. There should be a particular number of pi electrons. According to Huckel formula, Huckel rule, a molecule must have 4n plus 2 pi electrons to be aromatic. Any aromatic compound must contain 4n plus 2 pi electrons. N should be 0, 1, 2, and so on, so forth. So this is must that for aromaticity, that a molecule must contain this number of electrons. That is, cyclic, planar, and completely conjugated compounds that contain 4n pi electrons are specially unstable and are said to be anti-aromatic. Those cyclic, planar, and completely conjugated compounds that contain 4n pi electrons, they are very much unstable and they are called anti-aromatic. Benzene is aromatic and specially stable because it contains 6 pi electrons. Cyclobutadiene is anti-aromatic and specially unstable because it contains 4 pi electrons. It is anti-aromatic and very much unstable. Here, 4n plus 2, 4 plus 2, 6. 6 pi electrons, 4n, 4 pi electrons, anti-aromatic. So according to the Huckel rule, the number of electrons should be these are the number of pi electrons in a molecule should be according to this. And it is the number of pi electrons, not the number of atoms in a particular ring. N 0, so the 4n plus 2 pi electrons, 1 6 pi electrons, 2 10, 3 14, 4 18, and so on. So a molecule to be aromatic must contain 2, 6, 10, 14, or 18 pi electrons. Considering aromaticity, a compound can be classified in one of 3 ways. A cyclic, planar, completely conjugated compound with 4n plus 2 pi electrons. Anti-aromatic, a cyclic, planar, completely conjugated compound with 4n pi electrons. Not aromatic, non-aromatic, A compound that lacks one or more of the following requirements for aromaticity, being cyclic, planar, and completely conjugated. So a compound will be non-aromatic if it is not cyclic, or if it is not planar, or if it is not completely conjugated. So the aromatic compound must be cyclic, planar, completely conjugated, and must have 4n plus 2 pi electrons. And if these conditions are not fulfilled, so that compound will not be an aromatic compound. The relationship between each compound type and a similar open chain molecule having the same number of pi electrons. An aromatic compound is more stable than a similar acyclic compound having the same number of pi electrons. Benzene is more stable than 1,3,5-hexatriene. An anti-aromatic compound is less stable than a cyclic compound having the same number of pi electrons. Cyclobutadiene is less stable than 1,3-butadiene. A compound that is not aromatic is similar in stability to an acyclic compound having the same number of pi electrons. 1,3-cyclohexadiene is similar in stability to cis-cis-2,4-hexadiene, so it is not aromatic. Now, there are three conclusions. The aromatic compound will be more stable than the acyclic analog. An anti-aromatic compound will be less stable than the acyclic analog. And the non-aromatic compound will have the same stability as the open chain compound. Like here, benzene, more stable, aromatic, 135, then 135-hexatriene. Cyclobutadiene, less stable, anti-aromatic, 1,3-butadiene. And 1,3-cyclohexadiene and cis-cis-2,4-hexadiene, they have similar stability, so this is non-aromatic. Completely aromatic rings completely conjugated rings larger than benzene are also aromatic if they are planar and have 4n plus 2 pi electrons. Hydrocarbons containing a single ring with alternating double bond and single bonds are called annulenes. To name an annuline, indicate the number of atoms in the ring in the brackets and add the word annuline. Like it is 14 annuline. It has 14 pi electrons, so it's aromatic. It is an 18 annuline and it has 18 pi electrons, so it is aromatic. 10 annuline has 10 pi electrons which satisfy Huckel's rule, but a planar molecule would place the two hydrogens inside the ring too close to each other, thus the ring puckers to relieve the strain. Since 10 annuline is not planar, the 10 pi electrons cannot delocalize over the entire ring and is not aromatic. These two hydrogens this satisfy all the 10 annuline satisfy all the conditions for the aromaticity, except that due to the very much near vicinity of these two hydrogens, it cannot be planar, and so it is not aromatic. Two or more six-membered rings with alternating double bond and single bonds can be fused together to form polycyclic aromatic hydrocarbons, PAHs. There are two different ways to join the three rings together, forming anthracene and phenanthrene. These are the two rings, naphthalene, 3 rings, anthracene, 14, or phenanthrene. As the number of fused rings increases, the number of resonance structure increases. Naphthalene is a hybrid of 3 resonance structures, whereas benzene is a hybrid of these. Benzene is a hybrid of 2, while naphthalene is a hybrid of 3. Physical properties of the aromatic compounds. Melting point. More symmetrical than corresponding alkane, pack better into crystals, so higher melting points. Depending upon dipole moments, so ortho, meta, para for disubstituted benzenes. More dense than non-aromatics, less dense than water, and generally insoluble in water. Thank you so much. Thank you very much.